Hello, this is Dr. Brown. In this video, which is going to be relatively short, we're going to talk about the derivatives of inverse trig functions. Now, in pre-calculus, you've already talked about inverse trig functions. First, let us look at the 6 trig functions and talk about their inverses. Here you see a graph of sine of x, cosine of x, tangent of x, and cotangent of x. And on the next sheet we'll show one of secant and cosecant. But taking a look at these 4 functions, if a function is to have an inverse function, that they must pass the horizontal line test. And obviously the sine x, because it's periodic, does not pass the horizontal line test unless you restrict the domain to a certain range. And so, as you probably already know or should already know, if we restrict the domain of the sine function to go between minus pi over 2 and plus pi over 2, then it will pass the horizontal line test. Similarly, if we restrict the domain of the tangent function to go between 0 and pi, and just talk about this section of the cosine function, it will have an inverse. For the tangent function, if we restrict the domain to be between minus pi over 2 and plus pi over 2, it will also have an inverse. And if you look in the literature, there are several ways to do the cotangent function. In most textbooks, they would restrict the domain to go over this range, which would be 0 to pi. Alternatively, I have seen them restricted to be from here, which would be minus pi over 2 to 0, and then 0 to pi over 2. Looking at the secant function, we would have to restrict the domain to be from 0 to pi over 2, and then from pi over 2 to pi. With this restriction, the secant function would have an inverse. And for the cosecant function, it's pretty obvious we need to restrict the domain to be, as I'm outlining here, between minus pi over 2 to plus pi over 2. Now, if we go and plot the inverses of these 4 functions, we see the inverse sine function looks like this, the inverse cosine function, and the inverse tan function, and the inverse cotan function. This is one version of it, and I'll show you the other version on the other slide. Basically, all that was done was to interchange the x and y axis and replot the functions. And what we see down here is the alternate version, or one of the alternate versions of the inverse cotangent functions. And then we see, as we've already written down, the inverse sine, inverse cosine, and inverse tangent. And finally, we see the inverse secant function and the inverse cosecant function. And as you can see, you can imagine that these functions would have a derivative, and you could imagine drawing tangent lines for all of these functions. In fact, going back, obviously the inverse sine function would have a tangent line at anywhere in its domain. The inverse tangent function would have tangent lines anywhere in its domain. So that's what we plan to do, is derive the derivative of at least 3 of these functions and then show you the formula for the other 3. So first, let's figure out what the derivative of the inverse sine function is. And we're going to use implicit differentiation in order to do this. So we write down that y equals inverse sine of x. Now you know that that means, because of the definition of what the inverse sine function is, that x must equal sine of y. So now I'm going to use implicit differentiation and take d dx of both sides so d dx of sine of y is going to be cosine of y dy dx using the chain rule. And of course, on the other side, d dx of x is 1. So looking at 1 equals the cosine of y times dy dx, we can solve for dy dx, which is a derivative of the inverse sine function, equals 1 over cosine of y. So now we have a formula for dy dx in terms of the cosine of y, but we would like to have this in terms of x. In order to get that relationship, we go back and we look at the fact that x equals sine of y, and we also remember from some of our identities in pre-cal that sine squared of y plus cosine squared of y equals 1. Well, sine of y is equal to x, so sine squared y is equal to x squared. So add that to cosine squared of y equal to 1. We can solve for cosine squared of y equals 1 minus x squared. And so cosine of y is equal to the square root of 1 minus x squared. And if we plug that in to our derivative, we get dy dx is equal to 1 over the square root of 1 minus x squared. So our major derivation is that d dx of inverse sine of x is equal to 1 over the square root of 1 minus x squared. Now to do the inverse cosine function, we do it very similarly to the way we did the inverse sine. So we write down y equal inverse cosine of x, which means that x is equal to cosine of y. Now doing implicit differentiation, d dx of x equals d dx of cosine of y. d dx of cosine of y is equal to minus sine of y dy dx. And of course on the left hand side, d dx of x is equal to 1. And now we can solve for dy dx to be minus 1 over sine of y. And now going back and realizing that sine squared of y plus cosine squared of y equal 1. And cosine of y is x, so we have sine squared of y plus x squared equal 1. Sine squared of y equals 1 minus x squared. So sine of y equals the square root of 1 minus x squared. We can plug that into this equation and get dy dx is minus 1 over the square root of 1 minus x squared. So our result here is that d dx of the inverse cosine function of x equals minus 1 divided by the square root of 1 minus x squared. Now the last derivation we're going to do is for the inverse tangent function. And we will write down that y equals the inverse tangent of x. And of course, this definition means that x is equal to the tangent of y. Now taking d dx of both sides, d dx of tangent of y is going to be secant squared of y dy dx, and then d dx over here on the left hand side of x is just 1, and so you can see solving for dy dx, we get dy dx is 1 over secant squared of y. Now we would like to get this in terms of x. Here we have to make use of another well-known formula or identity from pre-calculus. Tangent squared of y plus 1 is equal to secant squared of y. And because tangent of y is x, tangent squared of y is x squared. So we get x squared plus 1 is equal to secant squared of y. So secant squared is 1 minus x, 1 plus x squared, and we plug that into this formula, and we get dy dx is equal to 1 over 1 plus x squared. So the major conclusion here is that d dx of inverse tangent of x is equal to 1 over 1 plus x squared. And that is the last derivation we're going to do. On the next page, I have put together a table of the first 3 derivations that we did, and I have written down formulas for the derivative of inverse secant of x, inverse cosecant of x, and inverse cotangent of x. Now the last thing we're going to do is work a couple of problems using our formulas. Remember, d dx of inverse sine of x is equal to 1 over the square root of 1 minus x squared. Now obviously in this problem we're going to have to use the chain rule. Our u is going to be x cubed plus 2x. So d dx of inverse sine of x cubed plus 2x is going to be 1 divided by the square root of u squared, which is going to be 1 minus x cubed plus 2x quantity squared times, using the chain rule, d dx of x cubed plus 2x. And so this becomes 3x squared plus 2 divided by the square root of 1 minus x cubed plus 2x quantity squared. And then the last problem is going to be taking d dx of inverse tangent of x squared. Recall the formula for the derivative of inverse tangent of x is 1 over 1 plus x squared. So d dx of inverse tangent of x squared is going to be 1 over 1 plus, of course our u in this case is x squared, so this is going to be x squared squared times d dx using the chain rule of our u, which is x squared, and this simply becomes 2x over 1 plus x to the fourth. And that's our video on the derivative of inverse trig functions.